So thank you very much for the kind invitation to and the kind introduction, and I'd like to thank you all for attending. I'm Michael Ferris. I sit in the Computer Sciences Department and upstairs in the Wisconsin Institute for Discovery. And the work that I'm going to describe today is joint work with Andy Philpott, who was my former advisor from the University of Auckland in New Zealand. It will become apparent why he's my colleague in this. So this talk is about planning problems for renewable electricity generation. And I'm going to talk while I'm subtitling it, Keeping the Lights On. I'm going to talk mostly about modeling and the trade-offs that occur when you have to deal with economic and physical and environmental issues all at once. So there's trade-offs that occur, and that's what I'm going to highlight within this talk. What I will do is I will try to formulate and engage you in thinking about some mathematical optimization models that are used or usable for advising economic policy and government policy. And I will tell you a little bit about uncertainty and how we think about uncertainty within these problems and how to represent decisions within a planning process. So that's what I'm going to try to talk about. And here's the first idea. So the idea is keeping the lights on. So the basic idea is we actually have supply of electricity, a bunch of generators over here, and we actually have demand or load locations over here, homes, offices, factories, or whatever. And the basic premise of the engineering problem is how to satisfy the demand with the supply. So there are physical constraints associated with this problem, and those physical constraints are about the properties of the devices that are being used to generate the electricity, and also characteristics of the network which is used to actually transport or transmit the electricity from the generation, the supply, to the demand. Cool. Physics, engineering, we all know how to do that. We can build models that actually do that. There's another issue here, and the other issue here is the smoke that is coming out the top of these generators causes environmental concerns. And so what we want to think about within our models are the trade-offs between the economic efficiency. We have an engineering problem. We actually want to deal with that engineering problem at minimum cost. We actually want to deliver the electricity at minimum cost. And so engineering, economics, and then we have an environmental constraint which says that can we do something about this smoke or these other carbon emitting generators or whatever, and can we go to a renewable system? So with that, just over a year ago, I went to New Zealand on a sabbatical. I was hoping to watch rugby, watch cricket, swim on the beach, and all of the things that you want to do in New Zealand. And instead, within 3 days of arriving in New Zealand, the newly elected Prime Minister Jacinda Ardern of New Zealand announced an agreement that her newly elected ruling Labour Party had made with the Green Party. And I'd like to bring out two features of that agreement that came out within 3 days, which then changed the course of all of the work that I did in the 6 months that we were in New Zealand. So the first point was that she was making a request to the Climate Commission to plan. So we're talking about plans, and the plan was to transition to 100% renewable electricity system by 2035. So you've not missed anything at this stage. We're just talking about going renewable by 2035. So that's the first thing. And then as a typical politician, then there were these caveats that they made, that actually geothermal, which actually does give a lot of carbon emissions, but geothermal counts as a renewable technology. And then there was also this caveat that this would occur in a normal hydrological year, whatever that means. And so hopefully I'll at least illuminate you what you could interpret a normal hydrological year. And the second thing that she was wanting to do was to do this carrot of 100 million New Zealand dollars, carrot to, as a green investment fund to stimulate private investment of the form of $1 billion. And so that we're trying to stimulate some new investment, and that investment was going to be an investment in low carbon industries. So the part of this talk, or the part of the work that I'm going to talk about here, is how do we generate models to get at the heart of what these two agreements or these two statements in the agreement are. So I want to tell you a little bit about models for the what and the how related to those questions. I'm quite happy to take questions at any stage if you feel encouraged or obliged. I would rather, if you have a beer in your hand, that might also help. Okay, so that's the question. So the first thing is 2035. We have to make a decision about 2035. That's a while away. And so there's a lot of data uncertainty. How much will the demand be? So we're talking about satisfying all the demand. What's going to happen? So you can go away and you can ask 14 experts. Talk to 14 experts and say, what is going to be the demand for electricity? How much uptake is there going to be of electrical vehicles within New Zealand, and how much change is there going to be in these technologies? And if you ask 14 experts, they will come up with 14 different estimates of what the demand is. And then you construct your optimization stuff, and you can go away and solve with those 14 estimates 14 different plans to come up with the distributions of the new technologies, of the different types of technologies you're going to use to satisfy this and whatever other constraints you have, maybe the economic or environmental. So we actually have 14, at least in here, we have 14 different futures or scenarios of the future, and I'll use throughout any talks when I talk about any mathematics, I'll think of omega as being a sample of a future, a view of a particular future, and here's 14 views of the future here. And the question is that now, well, we have 14 plans. Which one of these should we use? And I'd like to encourage you to say that we shouldn't use any of them. But what we need to do is we need to think about a strategy that takes into account this uncertainty, and just like we do in financial modeling, think about hedging. So actually coming up with a strategy which allows us to hedge, so to make a decision that we can and have a recourse action to actually recover from if we make a slightly incorrect decision. So, cool. So, first thing, we don't know the data. Second thing is, what does that statement 100% or fully renewable mean? Before I'm going to talk about that, let me talk about this picture and set this context of what I'm going to do within the modeling in terms of the context of this is my New Zealand plan. Okay? So New Zealand, as you all know, is made up of two islands, the South Island and the North Island, and they're far away from anywhere else. Okay, so there's no import or export of electricity because it's a long way away from anywhere else. The South Island is the place that you should go as a tourist. It's very pretty, lots of things, and in particular, there's lots of rivers with big hydro reservoirs on them. So big dams, which are being used to generate 55% of the electricity of New Zealand, comes from a hydro system. And so this is my little pictures of the hydro dams and how they're connected. So all of the supply, well, not all of the supply, but a large amount of the renewable supply is down here in the South Island. Unfortunately, most of the people are up here in the North Island, so 40% of the population live in Auckland, and so all of the people are up here, and so most of the demand for electricity is also in the North Island. So there's the problem as well. The problem is we're talking about renewable energy, And also in the North Island, fairly close to the demand, is actually the biggest power plant. So there are two power plants, a coal and a gas turbine power plant, which are the big non-renewable forms of energy in New Zealand are here. So if we're talking about closing down things, this is primarily what we're talking about, closing down. Electricity, we saw in the first picture, supply, demand. So the supply is over here, a lot of the demand is over here, so we have to get it through here. So I have this other node, H. So this represents my electrical network of New Zealand. It just has two lines in it. Obviously, that's a simplification, a modeling simplification. And H, you could think of, stands for halfway. It actually doesn't. It stands for Haywards, which is another power generating place. But anyway, H is halfway. It's just in the bottom of the North Island, and so it's over the Cook Strait, which is the water which divides the North Island from the South Island. Cook is that famous guy from a place where I come from, right? Right. So this is a transmission. There's a capacity link on here because the electricity has to go across the Cook Straits, and so it actually goes on lines under the sea. Okay. There's also some capacity constraints between once it gets onto the North Island, how you distribute it to all of the people. So that's the part of the problem. This is the context of the model that we're actually going to generate. And the question was fully renewable. Okay, so what could we talk about? Well, there's the blue viewpoint here, which is about shutting down capability. So you could actually close down or reduce capacity, close down the darn plants. So if you close down the plants, they're not going to be spewing out all of that smoke. And so this would be a way of becoming 100% renewable. So 100% renewable could be get rid of all of the non-renewable plants by closing them down. So that's one option. But the other option is that, reduce capacity. The other option is, well, what's the real reason that we're doing this? Well, we're worried about the stuff which is going out into the atmosphere, so that we want to control the greenhouse gases. And so is our objective to actually just close down plants, or is our objective to actually control the greenhouse gas emissions? And I claim that those are not the same. So in particular, because of uncertainty in the system, because of randomness or those unknown futures, closing down plants is not the same as reducing emissions. So if you close them all down, go to 100% closing down of everything is the same as getting rid of all the greenhouse gas emissions. So 100% might be, but if you only go to 95%, then it could be radically different. So here's the idea. So those hydro, so we want to hedge. We have uncertainty. We don't know. What's the problem with the water? The problem with the water is that it doesn't rain in the winter sometimes. You have a dry winter. And because of all of that hydro is generating all the electricity, if you don't have any water, you can't release it to generate the electricity. So the problem is the uncertainty which we're dealing with is low inflows into our power system. And when we have low inflows, then we have to use our non-renewable sources, our coal and our gas plants. If we have a lot of them, bully ho, we'll go ahead and use them. We have enough to deal with whatever comes up, and we'll do that. If we've reduced the capacity of them, then suddenly, when we come into the situation, the unlikely but possible situation that we've had a dry winter, then suddenly we don't have enough capacity left for our coal, from our coal and our gas, to actually to make up for the deficit between the water that we've stored in our big hydro battery and the amount of electricity we have. And so we have to lose load, or we have to do other things. We have no real recourse. So the recourse that we do instead is that we will store more water in the summer in case we have a dry winter. So we hedge against the bad uncertainty by storing, and you can see here, when we have no Huntley here, we store more energy or more water in the distribution across all of our different scenarios. On average, we store more water than we store over here because we have less recourse. Because we're storing more water, we're not using that water in the summer to generate, so we're using our smaller, dirty plants more frequently to replace that so that we can store it. And so we burn fuel to increase the burning fuel achieves the increased storage so that we can reduce or increase the emissions because we are storing water and not using that water renewably to actually generate electricity. So we store more water as a hedge against a dry winter. And because we were storing that water, we can't generate electricity with the water, so we use some dirty or some non-renewable source, and therefore we burn it. And so by reducing the capacity of our coal plants, we end up using the reduced capacity more frequently and end up with higher emissions. Yeah?
Super naive question.
Yeah.
Why don't you just turn on the coal plants when it's dry in the winter if you need them?
So they're not, if you have big enough capacity,
okay, but with
and you haven't
capacity, you can't.
Yes,
okay.
so it's just that you've already shut it down, you've shut it down too much, and that's the nice thing about keeping it open, is that you have that capacity to do exactly what you claim is naive, but is not really naive. Any other questions? Yeah.
Yeah, I was wondering, is there any way of recycling the water that's used in a hydroelectric station?
So this is the notion of pumped storage. So people do talk about pumped storage always, and then so you actually let the water come through, and then when it's cheap to actually pump it back up, you can pump it back up over that. New Zealand doesn't do that at this stage, just because they have so much hydro that what they'll do, instead of releasing it and then moving it back up at a later time when you have cheap stuff, is that they typically store it up there for a longer period as a hedge. But this is dominated by the uncertainty that we have to predict when it's going to be a dry winter or not. Any other questions? Yeah?
For reference, can you tell us when peak demand times are in New Zealand for electricity?
So peak demand, so it follows similar patterns. Typically, the peak demand is early in the morning and late at night. It's
on an annual basis.
So peak is actually in the winter. So heating is the major issue. There's not a huge amount of
electric heat. Okay.
Yeah, electric heat is predominantly used in the winter, and so there's no gas heating most of the time. Okay, cool. We'll come back in a minute. By that time, I will give you a new slide. Any other questions? Okay. Uncertainty. I've told you about uncertainty in demand growth. That's on the scale of years. We don't know what's happening in 2035. I've talked to you about uncertainty in rainfall, seasonal inflows. That occurs on the matter of weeks or months. There's also levels of wind and solar generation, and those are short term. Typically, we can predict wind or solar to the average amounts of wind or solar with increasing efficiency at half-hour timescales. And then there's the very short-term effects, which are a cloud comes over and obscures the sun, or my plant fails, or one of my transmission lines catches on fire, and so those are random effects which occur at the seconds. So we actually have a whole gamut of uncertainty which goes from years into seconds. So all of the models that I'm going to talk about have to deal with all of those timescales. So they're big models. Okay, so that's the first thing. We have big models to deal with the uncertainty of the data. The second thing is that in terms of investment, let's think about if you invest in a green technology. So you're going to invest in wind. So I'm going to make a huge investment up front. That's an investment cost. And how do I recover that cost? I recover that cost by generating electricity and get it paid for within the market. What does the market pay? Typically, markets that we have right now pay at marginal price. So they essentially pay about your operating costs. They don't really pay back your investment cost, what happens is you use uncertain events when the price goes up very high to actually recover your investment. So operating costs go down because renewable is real cheap. There's no fuel costs associated with it, but investment is going up. And so we have this trade-off between building more capacity costs more, but then it allows your operations to be cheaper. And so how do we trade this off and make sure that the people who we're wanting to get to make this $100 or $1 billion investment actually get recompensed for their efforts in here? And this is exactly what I believe the CleanTech Forum is thinking about, investment problems. So how do we spur investment by making sure that people can pay for it or recover their costs? So this is the math. Okay, very simplified version of the math. Okay, and so let's think about that capacity. So I'm going to install new capacity. That capacity is going to be X. It's going to cost me some K of X, some function. This tells me how much it's going to cost to do the investment. So this is the investment. And then once I've got it installed, the X, in each of those different scenarios, each of those different futures, I'm going to operate it at Y. And so Y of omega is going to be less than or equal to X because I can't operate it more than I have it. Okay, that's going to cost me C of Y. So that's going to be kind of a random variable depending upon which future I find myself in. Okay, and so what I'm going to do is I'm going to then think about taking the expectation or the average of those costs. So this is the expected operating cost, and this is the capital cost of investment, and I'm going to try and minimize this. This is an economic model. We're trying to do this at minimum cost. Now then there's this problem that if there's a demand omega, and if I suddenly get a big demand in some scenario because it's very cold this winter, and we end up with a big demand in omega, then my operation might not be enough to satisfy that demand, so I actually have to have some Q, which is the lost load. So I cut some of you off, and so the model allows you to cut you off, and then if you cut you off, then you have the value of that lost load. How much am I going to have to pay you because I didn't give you your electricity? So typically this is done on an industrial scale, and this model has simplification, but this is things called demand response and everything are mechanisms to actually work out what this appropriate value is and how we would implement this in detail. Cool, so minimize capital costs plus the expected operating cost. That's the kind of model that we actually want to do. That's the economic. This will capture all of the engineering stuff, so there's some other constraints in here. And then I have added to that the environmental constraints. So this environmental constraint then actually trades off the objective function against the constraint. And so here I'm saying the non-renewable capacity that I have to have has to be less than or equal to some fraction, 1 minus theta, of the renewable technology that I have, or the non-renewable capacity that I have in 2017. So I could think about another constraint. I could write that as a capacity constraint. That's the shutting down of plants constraint. Or I could write that constraint as talking about CO2, the amount of CO2 reduction. So based upon some function here, the amount of CO2 reduction, the amount of CO2 I have in 2035 has to be less than or equal to some fraction times the amount of CO2 reductions I have in 2017. So you can impose all different types of constraints into this model here. Cool, okay. So that's cool. Trade-off. The trade-off here is economic versus environmental. Engineering is captured in all of the data that we actually have.
What are the two stages of this? Okay.
So the two stage is a capacity, so it's an investment problem and operation. So it's here and now, we make the capacity investment, and then we operate it forever in all of these uncertain futures. So the investment and operation. Okay, so maybe you could have a staged investment, and so you would have a multi-stage, not a two-stage problem, but at this stage we have those models, but for the purpose of this talk it's a two-stage model. Any other questions? No. Cool. So So does this work? So let's think about this. We have graphs here, and along the bottom is that theta value. So we go from 0, which is business as usual, but this is business as usual in 2035, and then 50% right up to 95%, 99%, 100% renewable. So what do you see? Well, you see that the investment cost is going up. As you go more and more renewable, the investment cost, so you're going to have to introduce more and more expensive renewable technology until you get to here, and then suddenly what you see is that there's a maintenance cost which is pretty standard. The maintenance cost has gone down. The operational cost, if you can see, it's actually minimal, but it's actually gone down slightly, the operational cost, because it's getting cheaper because we're using renewable technology. But then suddenly, when you go to 100% renewable, you start shedding load, because there are some unfortunate scenarios when it's not worthwhile spending a lot more money to invest in this technology, and so you end up in those scenarios just losing load, and that costs you a lot of money because people are very unhappy when you switch off their electricity. So we can use this, and so what's happening is there's this trade-off between the capital investment and the operating cost. So we're using this fact to actually spur this investment. And so this fact that people are willing or losing all of this money will spur the investment, and that's the drive behind investment problems, is that you use the costs that people are incurring in an operational environment to incur or encourage an investment. So, but the investment here, the optimal solution says it wasn't actually worthwhile making more investment here. It was cheaper just to lose all of this investment. Yes?
So given that the inconvenience factor is such a big part of why that load
Yeah.
up, is there thought, or is it already anticipated in these models, of a decentralized backup system like my car battery can get me through a 12-hour outage or whatever to
So this,
change that?
so this includes demand response.
Oh, exactly.
And so there's demand response, but in this particular model, the demand response was more expensive to actually incur than, so it actually chose to do this. So in New Zealand, for example, the demand response, you can do it in industrial scale. So they have these aluminium, not aluminum, but aluminium smelters, which you can actually turn down. So, but it turns out that in these models, they weren't being used for that. It was still better economically at this stage. So it's not behaviorally, but economically it was better to actually cut off some of that load. And so typically this was industrial load and not consumer load. And so you get one person, yeah. So, yes.
A slight variation, I think, on Lori's question. Does the model look different if you look at diversifying the investment, so there are multiple kinds of renewables, like if there's 5 kinds of renewables versus 2 kinds of renewables?
Yes. So the model, so this is just the cost, and so I need to show you what is actually the portfolio of these investments, and so that's coming up in the model. I'm just telling you that at this stage, there is some way of formulating or paying back the investment, but it's only when we get really very green, 100% renewable, and maybe we don't want to do 100% renewable because it becomes very expensive. So this is 8 billion New Zealand dollars. So that was not very politically, considered very politically. Can we do it though? So does this reduce the CO2 emissions? So if I impose the constraint, which says that the amount of CO2 reductions go down, yeah, they go down, it works. My mathematical model actually solves the problem, and you can actually come up with a portfolio of different renewable technologies, which I'll show you on the next slide, but that portfolio of technologies actually allows you to reduce this. Okay, cool, so we can go down to completely in the energy sector, because we have this huge hydro battery, we can actually go down to 0 emissions, carbon emissions in New Zealand.
What's the unit on the y-axis?
It's kilotons of CO2. So this is something like, yeah, a lot. Yeah. So yeah, this is kilotons, and so it's something like 16 megatons of CO2 equivalent. But fairly big. Yeah, so that number, this number here, 16 is 16 megatons. Okay, so quite a bit of electricity, and you can get from 16 megatons down to 0. Okay, well now, but if you think about what the politicians say, well, we can change the rules. We can say we'll talk about not just reducing the CO2 emissions, but let's talk about doing what everybody, the green people, tell us to do. Let's shut down the plants. So the blue line talks about shutting down the plants. Well, if you shut down the plants and you shut down only non-renewable plants, and by the way, geothermal and carbon capture with storage, well, that's renewable. Okay, then you shut down those, and the CO2 emissions do go down. You can do this a lot more cheaply, and they do go down, but their amount of reduction isn't going to 0 because geothermal and CCS still do emit carbon dioxide, and so when you do this, you actually only get about a 50% reduction. So you can do it cheaply if you change the rules, or more cheaply. You'll get a different distribution of the technologies, but you don't achieve, if this is your goal to get to 0 CO2 emissions, then you don't get it. Furthermore, remember, getting to the 0 here was really expensive. Okay, so Laura asked, well, what technologies do you want to use? So we have a whole swath of technologies that are possible technologies that you can incorporate. And if you have your favorite technology, it's either in the model and wasn't ever chosen, so it's not in the key, or I didn't implement it in this particular model. So again, we're going here. So this is the capacity mix. So this is megawatt hours, I think, in some scale. I don't know what that scale is. And the ones at the bottom are the non-renewables. Those are the things that we actually want to kick out. So when we're doing CO2 reduction, we want to get rid of geothermal, we want to get rid of OCGT, open cycle gas turbines. Green is closed cycle gas turbines. Blue is diesel. By 2035, New Zealand has already said that they're going to get rid of all of the coal anyway, so it's not even in our original model, so we don't have to close it down because it's already somebody's decided to close it down. Okay, so we want to get rid of those, and so we gradually get rid of those until we get to 100% renewable. What do we add? We add a lot of wind. If we add a lot of wind, we actually have to worry about when we're needing that load, and so we actually have to have our batteries. Well, our hydro is the battery, which can move energy from one period to another period, but that's not enough. We have to add some other slow batteries. Slow batteries are dorky batteries, cheap, but they can actually move electricity slowly. The rate is rate limited. It's not worth going to fast batteries. It's not worth doing demand response. In particular, it's not worth, all of us greenies who want to put solar on our rooftops, this is not viable. The model says that this is not the right way of becoming green. Okay, and so even if you do this, the expense there comes in here, and here's the portfolio. What we do is we have to increase the capacity, but the capacity is increased essentially because of the unreliability of wind. You have to put a lot more wind in case the wind doesn't blow all the time. We have to have enough over the whole of New Zealand. We have to have enough installed capacity to meet the demand. So that's why the capacity goes up. If you instead, say in doing CO2, you say just close down those bad guys, these bad guys down in here, but say, well, we don't need to close down the geothermal because Jacinda says that that's renewable. Okay, then you can actually reduce the capacity you need. You can actually put in some CCS because the CCS is now considered a renewable technology. It is better than coal and open cycle gas and closed cycle or whatever. It's better than those things, but you end up reducing the capacity that you need. You don't need some more because it's not so uncertain in the future. So therefore it's cheaper. Okay, so if you look at the cost, when we do the blue or the orange, I haven't really talked about the blue, but the blue is the closing down of things. Because we're changing the rules, we can do this much more cheaply. And so instead of going from, so the cost goes from 1 billion up to about 1.1 billion. So you can be 100% renewable if it's just about the capacities of those plants. But if you actually want to deal with the CO2 or the greenhouse gas emissions, then it goes from about 1.1 up to whatever, 1.6, a 50% increase in cost. Cool. Except for if you then go with a different future, which says that actually 10% more of our cars will be electrified, which are taking out, we're bringing that extra 10% of those cars into my electrical system, then suddenly it becomes very much more expensive. And you've already seen that before. So the cost of actually reaching zero CO2 emissions without geothermal or CS increases as we approach the limit, and it gets very expensive here. Okay. So I'd like to finish off, and I'm sure I'm over time, but I'm going to finish off quickly now. Think about what this is in the context of the political discussion. So the political discussion is about emissions. And so New Zealand as a whole emits something like 80 megatons of CO2 equivalent per year. Okay, so there's a net, because they have lots of forests, there's a net decrease, so the net is something like 56 megatons of CO2 equivalent per year. Okay, there's this energy sector, that's what we're thinking we're dealing with. There's this big pink sector here, which is the agricultural sector. The Prime Minister, the decision maker here, says that this is off the table. Just like in Wisconsin, you can't deal with the agricultural problem, you're dealing with the energy problem. So instead of dealing with the 80 million ton problem, we're dealing with a 30 million ton problem. And that's where you saw the 50% reduction coming down to 15 megatons. Okay, but let's look at that. Let's expand this red box here. What are those 30 megatons coming from? Well, those 30 megatons are actually about 4.5 from energy industry. That's what we're worried about in this talk. And then there's about 15 million tons coming from transportation. So if we move the transportation, if we electrify our vehicles, then we'll bring a chunk of this into here, and then we'll deal with it. Okay? And yet we're talking about 5% of this, and we're spending a lot of money to deal with 5% of this. Well, let's see what that is. Well, if you think about those 4.5 million tons, a bunch of this is petroleum refining and manufacturing of solid fuels. That's not on the story here. When we come down to it, the actual amounts that we're dealing with are 3 megatons per year. Now you're saying, I want to go 100%. I want to remove all of this 100%. And I'm going to spend a boatload of money, instead of doing 95%, I'm going to spend a boatload of money to go from 95% to 100%. Is this worth it? The claim would be that we should look at abatement policies. So we should look at about mechanisms for taking some of the yellow or some of the pink back into this sector and reducing that by using incentives. So biofuels is not an effective energy resource, but if you couple the biofuels with the reduction of the CO2, then maybe with some incentives this becomes viable. Similarly, if you electrify your vehicles, that could actually lead to taking some of this stuff from here into this energy market. So you could take a chunk of this CO2 emissions, bring it into here, and even if you only do it at the 80% level, you can do that economically effectively and reduce the problem at all. So I believe that these models will actually give you some idea about what is the appropriate price for abatement. So we actually want to know what is the incentive that you need to give to that other sector in order to do what you're considering the right thing. So to conclude, what have I told you? I've told you 100% renewable electricity system has several interpretations. They're open to political debate. The politicians change the rules, and that's okay, but we should actually make sure that we build models that actually interpret and detail what are the effects of those different assumptions that you make in the model. You should make sure that you do the right thing. So by that, you're minimizing the right objective. So I showed you that if we minimized or closed down capacity, that could lead to an increase in emissions. So if our objective is to reduce emissions. Make sure that's the objective of your problem, and use not the action that you think will cause the result, but use the imposition of the result that you want to make sure that it happens. I claimed that uncertainty at multiple different timescales was really important, and hopefully I showed you some reasons why that was the case. We do have some fancy stuff that if you were a different audience, I could tell you about the mathematical tricks that we use to actually incorporate those, but I don't think there's beer over there, right? And so it would take a long time. If geothermal and CCS, carbon capture with storage, are actually renewable, then 100% is feasible. But I showed you the emission reduction was modest. You could actually force, for somewhat more a cost, you could force the reduction to 0 in CO2 emissions. But I claim that 100% emission reduction in New Zealand electricity is needlessly expensive when given the proportion or the other sectors where you could effect change and at a much more cheap marginal price. I mentioned that we could do these models in a multi-stage setting. You also have to worry that all of these generators are not owned by one person or one entity. So rather than forcing all of them to work as one entity, we have built some models which actually show how they work in a competitive environment, and the details of that are another talk. To conclude, I want to finish with another trade-off. And the other trade-off is that the connection is lost, but the other trade-off is that blue skies and green fields has the trade-off that we might have to have some different types of sculptures on our horizon in the future. So trade-offs are always necessary, and which are the right trade-offs are the things that we should be discussing here at the university. Thank you very much.